we're going to enter into phase 2 of these 3 phases talk. Okay. Someone, where is he? Oh, he's over there. Someone mentioned something I forgot to show you, so I will just show you now, but I will use it a bit more afterwards. I will just take that, okay, and I will go somewhere else. Maybe one of you knows this website. So it's gcc.godboard.org something. Just zoom a bit. Is it readable? Yep. Okay. And that's very funny. So that stuff you can actually shove code there. It gets compiled, and you can have a look at the assembly on the other side. And if you really don't want to do, you can actually see how other compilers on other architectures behave. Okay. That's very interesting things to do. It's very useful when you try. Oh, they got ICC now. Wonderful. That's very interesting because sometimes you have performance issues with expression template or not, and you doesn't have any freaking clue what's going on. And this stuff is actually very useful. Yeah, it zooms, but it's not very okay. Should I just zoom? Okay. Oh, okay. So it's either I zoom or I just dezoom everything. Okay. So if you look at there, basically what the stuff is doing is, I don't remember what I print. What do I print already? Yeah. So E is probably 8. And so, yeah. So if you look at this, yeah, I just put 8 into a register, put C out into the others, and I just call the insertion operator. It doesn't have any function calls there, okay? And if I lessen the optimization level, same there. Same there. So you really want to go low. And then now you start all the functions starting to appear into the assembly languages. So even in O1, we still get what we want, okay? But the fair assumption on this is that you have to rely, oh wait, no, sorry. You have to put your faith, into the ability of your compiler to perform a lot of inlining. Okay, if your compiler's inlining capabilities is bad, you will have probably bad surprises. Okay, so now, we went through all of this, and we saw that we have a way to build arbitrary tree at compile time containing information about the structure of an arbitrary expression. There is plenty of tricks you can do with this. One trick is that, for example, these assignment operators I showed a bit before, there is cases where it should be good if we have the assignment operator inside the tree. For example, let's say you want to optimize matrix operation of the form C times equal A times plus equal A times B, and you really want to capture that and send it to a proper BLAS level 3 operations. But for doing this, you need to capture C, A, and B. So by making the plus equal operation say something like, okay, I will evaluate something into what I need. Instead of evaluating A times B and putting it somehow into C, you will say, I will build the tree of plus equal assignment between C, A, and B and evaluate that. So sometimes you want to build an arbitrary bigger tree into some other operators before calling the compression points. Okay. So arbitrary functions called, arbitrary operator calls get translated into statically represented tree of the expressions that you can evaluate by doing some tree traversals. That's the basics. But that's the basics. And we have a lot of stuff to do. And one way to do this is to use tools for that. You don't really want to run your own expression template engine by hand. Well, you may want to. I strongly advise against it. Okay. For I tried to do this during my PhD and I almost died. Okay, so, and yeah, it's fun the first time. Well, it's fun the first time. Okay, and it's definitely not the second time and all the time afterwards. So it's better to rely on tools, okay? And one of the tools that happens to exist for this is Boost.PROTO. There was a bit much of an older tool that's called Pete and Puma. Maybe someone of you know about those names, which is basically the grand ancestor of that. So what's behind Boost.PROTO? As I say, writing manual expression template engines are quite limited. there is far too much boilerplate. If you really want to have something that has more than 2 operators on one terminal types, okay, forget about your weekends. And we have the problem that the data and the traversal of the data are tied together and are far too much coupled. And it's not easy to work with other similar but yet different expression template-based code, because we have no way to know which expression is coming from where, and you basically have to special case everything. But sometimes you really want to have this clean expression coming from library A into library B, which happens to be another expressions. But that means that B and A must share information about the representation of the tree. Not very practical. So the solution is to find a generic interface for expression templates. I was about to write concepts when I wrote that, but then I forgot about how tricky it could be. And this generic interface has to be generic enough so you can actually build arbitrary number of libraries based on expression templates, while knowing that they are all interoperable, but yet you can actually still, differentiate them. And what we need to do is to have a way to represent transformation of the tree in a more, let's say, friendly way. And one way to do this is to not reinvent the wheel and take pages from compilers and try to orchestrate your transformation into something that looks like compiler phases. And finally, we need to solve the extension issues, which is, what if I want to take one tree and turn it into something and take the exact same tree and process it into a completely different way without having to rewrite the your world each time? Okay. And that's what BoostProto tried to do. And to do this, we have to sit down a bit and look at the bigger picture. When I said, like 1 hour ago, that the primary use of expression templates was to limit temporary generation and improve performance, I lied. That's a very, 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 very limited view of what we can do. But the problem is, it takes us basically 12 years to understand that. Okay. The main objectives is find a way to implement something called domain-specific embedded languages. So first things first, what is a domain-specific language, or DSLs? It's usually a declarative language, which may or may not be Turing complete, that do only one thing. It's very good at solving one single family of problems. Okay, who use make? Sorry for you. No. So make, it's a DSL. It's a small language that lets you build system. Who use SQL? Yeah, same thing. You access databases, schema with that, but you probably can't write a build system using SQL. Okay, nobody contracted me. Oof. And who use MATLAB? Okay, same stuff. DSLs for solving issues of numerical computation. MATLAB is a bit more Turing complete than SQL or make, but that's the same idea. When you write with MATLAB, you doesn't write your frigging triple loop whenever you want to make a matrix multiplication. You just write, I want a matrix multiplication, and the system do it for you the proper way, or so what MathWorks says. So it solves only one family of problem, but it solves it the correct way because it only has one kind of problem to care about. And usually those kind of languages are either interpreted or compiled into something else with an external tools. So what are DSELs? Domain-specific, same stuff, but embedded languages. So embedded is a bit tricky. It doesn't make embedded like in embedded systems. It's embedded like in it's hidden. It's basically a library that took on his head, okay, the mantle of a language. It's a library which is designed with the same basic principle of a domain-specific languages. So instead of relying on providing an API based on objects and functions that do stuff, the basic design is driven by the fact that you want to build a library where the core element could be seen as a core element of a special languages, and the operators and the function you apply on them is made so that the code you write with it looks like an external languages embedded into your C++. That's what basically BoostProvo does. It looks like a Bacchus norm form inside C++. except it's just a library. And what we do with this is that we force our good old C++ compiler to be turned into, locally, a compiler for this DSL. That happens to generate C++ and then do whatever. And expression templates are actually the only solution we have right now to write something close to DSLs inside C++. And that's far more powerful than let's optimize a bunch of temporaries. That means that we can actually take a bunch of expressions and take decisions about code generation based on your successions of operation into these expressions. We can take it, slice it, rebuild it in a different way before we do anything. We will be able to pattern match inside it, and so on and so on. And that's the real usage of expression templates. What I said during the break is that if I have 5 minutes, which I don't, I could actually write a small DSL, expression template-based matrix library that prevent temporaries to happen. And I could probably write a similar code, but far less complex, using regular functions, regular operators, regular matrix types that use move semantic, RVO, and clever usage of all of this. And I'm pretty much sure that the performance will be quite close. That's an experiment I still have to do, but that's my gambit on that. So if the performance is not the main focus, why are we still doing this? So we need it, because we need to build arbitrary expression of an arbitrary language and turn it into something else. And the best way to do this is to capture your AST and take decision about it. Except you don't really want to do that all day long by yourself. And that's where BoostProto kicks in. BoostProto, it's an expression template toolkit. It gives you all the frigging boilerplates to get all the operators, all the functions, decorating the tree, knowing how you want to traverse the tree in one way or another, and it's all ready to use. You don't have to write any of the craft we said just before. We just generalize a way of implementing an expression template engine. And it's made so it's customizable. And it's also a compiler toolkit, because contrary to what we wrote very crudely in the first part of this talk, we use concepts to make phases into the systems. We will see that once we build an expression, we can match it against something that validates the fact that the expression is correct within our languages. That's what the rest of the world call a grammar. Okay? And then we could actually do something when we go down our tree and find some kind of patterns. That's what we call semantic action in the rest of the world. And that's terms that will come back into BoostProto and help us build those kind of, let's build a grammar that will chase this expression, and if it's correct, I will select which kind of semantic action I want to provide and apply on this and get the resulting code. And if you build different library based on BoostProto, you have a way to say, oh, this is this library and this is that library. I know what to do when they get mixed. They have to go into an expression of this other library, and so on. So we are be able to build interoperability between DSLs, which is very important. So because you really, really want your, let's say, your eigen computation to be put down inside the Phoenix functions passed to Boost Spirit, okay, stuff like this. So how does it work? Well, first task we need to do is, as we said before, we need to generate this damn tree from a bunch of code. That's basically all you need to write. That's replace these 80-something lines of code I wrote before. You include BoostProto, you make a terminal, done. And you instantly have all the operators and all the operators you want on your terminal. Every one of them, including the crooky comma operator, including the very strange function member access through arrow operator, whatever. Everything is already there. I can write this code like this, which doesn't make any sense. Okay, it will compile. Okay? It just has everything. And everything is instantly turned into a lazy tree as soon as at least one terminal defined as a BoostProto terminal is anywhere in the expression. So you just need one proto terminal to contaminate your expression and get a lazy version of it. Yes? That's what a terminal is. It has to be into a leaf position somewhere. That's a terminal, by definition. Oh, yeah. So the question is it really that much contaminating? Yeah, but the regular rule of the language happens. So the example was, what if you write x plus parents 3 plus 5? Well, the compiler will probably compute 3 plus 5 and replace it by 8, and you will end up with a tree which is x plus 8. But you end up with a tree which is x plus something. Okay, but the regular rules still apply. Yeah, the same way you cannot change the precedence of the operators, because the language doesn't let you to do so. Okay, so you can write this code, and we have this very dandy display expert function that do what is just written in the can. It just displays the expression. So if you compile that and run it, you end up with something like this, which is basically a laid out view of the tree you just built. Okay, and BoostProto just prints the name of the function tag every time they find one, and the terminal, you get the value printed as soon as the type you put into the terminal as a stream insertion operator. Okay, if not, you just print the type of the terminal. So you just do this, and you have basically 80% of what you need. You can build a tree and inspect it. Display expert is very interesting because you can actually play with your operators and see what makes sense in terms of your language design. And when you are okay with what you should be writing and matching, you can actually do whatever. So you have a terminal of int in the BoostProto terminal. Everywhere you put it, you just contaminate everything, and you get a tree. Okay. So, okay, nice. But what if I really want to do something with this tree? Because, like, you know, I'm not there to just displaying it. So that's a bit more complex. So I will switch to real code because this font is very, very, very too small. So which one is it? Okay, tree validation. So just so we see it there, okay, I can actually take it and put it there. Okay, so that's like 10 lines instead of 70 something. Not that bad. So BoostProto is currently something which runs on regular C++. Don't need 11 or 14, but just that I'm a lazy guy. So yeah, you got that. And you can do crooky thingy like this. For example, I think that's this way you do it. I never know how you should be writing that. Yeah, that should be do it. Yeah, I did something wrong. Come on. Oh, no, it's, yeah, okay. Oh, yeah, of course. Yeah. Just die. Okay, what about that? That should be doing it. Yeah, comma, plus, minus, plus, multiplies, blah, 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 and so on and so on. And what's the name of this funky arrow star? It's called the memptr. Okay, that's what we want. Okay, so you can just write that, and you just get captures all in itself. Okay, and I think you can also have stuff like this. And that, and so on and so on. You basically have everything. Oh yeah, including this in the middle. For compiler. Oh yeah, of course. Yeah, so rule number 1 with expression templates. It takes time to compile, it's probably correct. It returns directly, you made an error. And the issue is that I'm half joking, actually. Okay, comma, plus, minus, blah, blah, blah. Where are the new guys? memptr subscribed, it's the brackets, and function is this. So we got everything, okay? And function is a bit strange. I put a function operator with 3 stuff, and obviously the node is a full elements node. The first one being the one you call the function operator on it, okay? But you have everything, okay? And it just works. So back to this. So what I really want to do is I want to write a piece of code with some operators. I don't want to write a piece of code with whatever, because I want to limit the scope of my language, okay? So the first thing we need to do is find a way to say, I build an expression, and what I want to know is this expression correct with respect to my language design? So who already worked with designing a language there from scratch? Yeah, okay. So what you need is what we call a grammar. A grammar, we say, this is what is authorized in my languages. And if you don't do what I say, your expression or your statement, your program is invalid. So what we need to have is a way to take an arbitrary expression and check if it matches a grammar. Okay. And the way to do this is to use these funky operators. Look at line 11 and following. So we make a structure that say my expressions, my EPA, what can it be? It's either a terminal of underscore, which means a terminal of whatever types, or it's plus applied to two sub-expressions validating the same grammar, or multiplies between two elements of the validating the same grammar again. Okay? If I wrote that using a more classical way, I will probably have written something like this, which is that my EPA is it's either a terminal, okay, or it's an EPA plus an EPA, or it's EPA times EPA. My BNF is a bit rusty, but that should look like this, if I'm not mistaken and taking some shortcuts. And that's exactly what I just wrote, okay? Except I have to explain it with whatever syntax the C++ language lets me. So the idea is to say we have this OR matcher. We also have an AND, okay? That says this is what I accept as a valid language from you, okay? And if you look at the way it's done, you can actually refer to yourself inside. So you can have this EPA is an EPA of an EPA, okay? I could have wrote something like this, which have meant I want an EPA on the left and whatever on the right, and so on and so on. Okay. So we have a bunch of constructors like this that help us build a matching pattern of what is correct. Okay. So that's a very crude example. We will get through a very more complex one later. But yeah, it's actually a bit more than that. So obviously I use plus and multiply, but you have everything else. Okay, you have a constructor for every operators you want. You also have a generic matcher like binary expr, unary expr that say whatever the tag, whatever the operation, if it's binary, it's okay. Okay, and so on and so on. So what do we do with this structure? Okay. Well, we make a terminal of n there. And I'm asking if does x plus x, the type of x plus x, match the EPA grammar? Okay. And does the type of x divided by not x match it? Okay. So I just use Decker type there, okay, but you could have put it into a function and taking the type of your expression in another way, okay, just for the example. And obviously, the first match will return true because x plus x is basically terminal plus terminal. Terminal match EPA, so EPA plus EPA is matched recursively. Okay? And the other one is not because I don't have any device and I don't have any complements into the grammar. Okay? So if I take these things and I go there again, I should have true and false printed. Whenever you want. True and false. And, okay, I can actually, oh, sorry, I forgot about that. Yeah, tab. I should have made an IO manip say STD small screen, you know. Just that tab everywhere. Yeah, true, false. So what if I do this? I do that. Does it work? Should it and will it? Yeah, intuitively, tree has to be converted somehow into a terminal of int. That's what Proto does. As soon as you have something which is contaminating, everything else is bundled up into the proper Proto expression that match it. So tree is a literal, okay? So it's a terminal. So it should match terminal of whatever rules. That should be saying true. Let's see. Whenever you want. Okay, true. Okay. And I can actually add stuff there. So let's put divide backs. Divides. Okay, so I can write that. Okay. So that's just as simple as that. Just add your rules and done. And except it's not divides. What's the name of that? It's not. Oh yeah. Sorry. Oh yeah. Yeah. I forgot my usings. I should have put them. Because multiplies, you can, sometimes it doesn't know if it's multiplies or times, but divides is divides. I don't know how you can call it actually. And so now look at if I do this. Okay, let's make something more complex. So now I have a terminal of floats. Okay. Still works because we don't put any constraint on the terminal. Okay, and now let's what happens if I do this? You can actually write that. I want a terminal of float and nothing else. And the last one becomes false because 3 is an int, it's not a float. Okay. Let's go back there. Yeah, this is a terminal of int. Let's see if it's true. Let's see if our intuition is right. Oh, sorry, is right. Okay. Let's see if this compiles. Yeah, it compiles. Wait, what the heck? I wrote a grammar saying I don't want that to compile. If I match it, it says it doesn't match it. But when I print it, it just prints it like there is no tomorrow and doesn't care about the fact it's not a correct expression. What the heck is going on? Well, the fact is that proto matches is one kind of traversal of the tree that just happened to match it. But when you build it and you pass it to display expert, it just displays whatever you give it. Okay? It doesn't magically do anything more. Okay? So beware. So what we will be needing is, we will see that later, is a way to say, actually, I just don't want to match it. I just really want you to prevent the construction of this tree if it doesn't match anything. Okay? We go on that a bit later. But yeah, we can actually take a tree and do whatever we want. And matching a tree against the grammar is basically a recursive descent of the tree and match with the recursive definition of the grammar until something blew up. It's just a tree traversal. Same for displaying, just tree traversal. And tree traversal doesn't care about the fact your expression is valid for a given grammar. They just traverse the damn tree. Okay? First rules. Okay? So I can actually say, okay, is it correct that this is in the shape of a grammar? I think it is. So what do we do next? So next, we may want to do something with the tree, like evaluating it. Okay. So we have a very, very similar way of describing a transformation of a tree. It's called a transform. So what do you want to do? Whenever you find a terminal, you want the value. And whatever operation you get, you actually want the natural semantic of the C++ operator on it. If I do plus, I want to do the plus between my values. And if I do times, I want the times between my values, and so on, and so on, and so on. And that's exactly what we wrote there. Let's have a look in a more decent font. So it uses the exact same system as for the grammar, for a simple reason that a grammar is also a transform that happens to say yes or no is valid. It's the same thing. But what we will be doing is we will associate with each pattern of sub-expression an action. So when I match terminal of something, please give me the value of the terminal. That's what this underscore value means. Give me the value inside the terminal, whenever you find one. And that's one of the shortcuts that actually is built by Proto, is otherwise, for everything else, just call the default behavior. But before calling the default behavior, please call myself on whatever sub-expression you found. So that's what this default eval means. Evaluate every sub-expression with eval, and then apply the logical, basic semantic of the operator you found. Plus do plus, times do times, and so on and so on. So 2 lines there is basically all those operator function call we wrote into all our expressions in the part before. Just say that. And so what does it bring us? Oh, okay, it's in a structure, but what I really want is a function. Well, actually you got both. Eval is basically a callable function object. So you just make an instance of eval and you call it on an expression, just like this. Okay, you make AE and you call it on your expression. And this will recursively apply the pattern matching and do whatever you're asking him to do. Okay, what do you think will happen if I had 2 different rules, one for the terminal of anything and one for the terminal of float, for example, that for whatever reason returns 10 times the value, okay? One trick is that the orders of the rules inside the OR is important. They basically are matched from the top to the bottom, so you have to be careful of that, okay? So you probably want the most specialized one on the top and going down the tree like this. So this build for us these your recursive function call systems that will apply whatever transform you want on your tree. And again, doesn't care about the fact that your tree may be wrong. Just take the tree, apply whatever. Be careful with that too. So usually what you do is, either you get an expression that comes from you don't know where, and you will try to see with a static asset if it matches what you think it should be. And if it matches, then you apply your transform. Okay, that's one simple way to do it. So the magic behind or and when is basically it just, inherits from every element, providing either the function call operators that do the operation or doing the types checking for the grammar and so on and so on. But the interesting point is that a grammar and a transform is basically the same. A transform being a grammar where you basically add on each rules a semantic actions. Whenever I match this is what I want to do in a very straightforward way. And I could actually write a second evaluation scheme matching different stuff and passing them onto the same tree. That's basically what we wanted with the simple systems. I have a tree that is built by Proto, and I have a bunch of function objects that represent arbitrary operation on arbitrary trees. And I can take whichever I want into the transforms and apply it to whichever tree I want. It's completely decorrelated. Okay. So this means that you can have a grammar that matches something, a second one that matches something else, and a bunch of transforms, and you can call them all together on the same tree you want. Not a problem. Okay. So let's see if this thing works. Because it looks like that is doing nothing, but probably do something anyway. Oh, don't forget the tab. It's probably doing like, I don't know how much is that, 4699. Okay. And actually I could do this. Well, could be putting floats because if not, it doesn't make any sense. So it's probably some amount. Yeah, probably. Okay. I don't have to write anything else, I know. So yeah, we can do this. Okay. Oh yeah. And as I said, every operation is there, right? Okay. Any operation. So let's say we have that. Okay. And let's make a terminal of std array of, I don't know, 3 floats, something like this. Okay, here comes the funny parts. Let's play a game of how many braces. So I think that's enough. Like 5, 8, 99, okay? I don't really want to be narrowing anything, so that should be it. What? Sorry? What? Yeah, I rename. Wow, yeah, I just saw it. And so that means that I could probably do this because every operator has the default C++ semantics. So I guess this works. I will end up with a bracket operators, a tree with a subscribe between y and 0, and I ask him to be evaluated with a classical semantic, which we probably call bracket on the underlying array, and giving me, I don't know how many, 5, and I need it to 2, something like this. Should be working, okay? So that's live demo, bear with me. Okay, I clicked, thank you. That should be working. 7. And just so we are sure what we're speaking about, of course, what is there? What's the type of that? We know it's for obviously an expression. Cannot be anything else. If not, evil will have blow up already. But just to be sure. And so I can win 5 minutes of compilation time. So yeah, and look, okay, I will probably make some kind of effort because that's important. Do you see this? Everybody? Yeah? Okay, so it's plus between the terminal that contains 2 and the subscribed operator between 0 and this wonderful terminal of st5 array iflm3ee, which is basically the mangled name of std array of 3 floats. Okay? Yeah, so it did not evaluate y of bracket 0. It built a tree that say I will do it later. Okay, that's very important. Everything is lazy. Everything, from top to bottom. Yes, a question.
Yeah, so we can throw anything into this expression, whether it's valid or not for our DSL, correct?
Yeah.
So what's this? How is that possible? I mean, I could, if I change line 19 to be terminal of my cool class, and then I try to evaluate x comma x.
Yeah. It will probably call the basic operator comma on your classes, and if it doesn't have, it will just call the comma operator of the language. And if your cool classes as also, okay, sorry, the question was, what if I make a terminal of my cool class? Okay, what happens is that if your my cool class has operator plus times whatever, it will just call it. Done. Okay. So let's see what happens if I do y plus y, for example, because we obviously doesn't have a plus operator on std array, and I will answer you just afterwards. So I think that will probably blow up. If not, I will be disappointed. So this probably should not work. I hope. Yeah, okay. So when it blows up, it blows up. That's cool things, okay? So yeah, oh no, I was me. No match for operator plus between std array of something and std array of something. The default transform just say do whatever you should be doing with the operators. I don't care. Okay, but that's a shortcut. Okay, we will go over and see that actually you can do far more. But basically, if you don't need more than that, you just do the whatever you need to do. Okay, there was another question. Oh.
Do you always have to specify?
So the question is, in the terminal definition, like line 19, okay, should I could I use the underscore stuff and so I can shove whatever I want inside? No. You have to have a concrete types. But the concrete type can be boost any if you want. That's not an issue. But no, you cannot just wave and waves or whatever. But look at the things. That you have this terminal of float thing from which we extract this colon type line 19. And obviously, and obviously that's the same type than there. Okay, that's the same type. Cannot be anything else. I just did one using boost terminal. But that means what? It means that a terminal of something or a plus of something something, it's three things. It's a match pattern in the grammar. Is the object representing the expression as soon as I did colon type behind it. And it's also its own default transform. Plus of something something, put on the other side of a when, just do a plus on whatever it found. So it's three things. The transform, the grammar, the expression types. Okay? And everything is tied into a single block. Okay. That's the crooked things with BoostProto, because sometimes you look at the code and you are like, what is the heck is going on? I just write 3 times the same things with 3 times different meanings. That's the one thing you have to go over. Because if you think about it, it's normal. The tree definition is a way to represent the grammar it should match, and it contains the operation you should be doing when you traverse it. So having the tree semantics into the same block, different places, makes some sense. Keyword is sum. So what we should be doing next? Well, I really want to do something else than just calling the bloody operator from the language. So you can actually write a custom transform. Okay, so we are just pushing everything to 11 now. So let's have a look at this one. So same things at the beginning, okay? Except I just change a bit what everybody is doing. And I say that when I match a terminal of whatever, I want the value, like before. At the end, if I didn't match anything else, just do whatever the language should be doing. No problem. And you got this monster in the middle, which says, when I match a plus between two something, okay, what I want you to do is doing this. Okay, probably need to go back there. Okay. And what the heck is this thing? It actually reads like it should be doing. I want you to call the custom function on the evaluation of the left child and the evaluation of the right child. And okay, what does it look like? It looks like a function call, right? With round stuff. Except, cannot be a function call there, okay? So what it is, it's basically a function types, good old function types. So we use that to, mimic the fact that we want to call a function, okay? I don't remember if it's, who calls that round lambda? I don't remember. I have to dig that. So I want to call the custom function on the evaluation of my two sub-expressions. Okay, so left and right are actually shortcuts to the left child and the right child. It's the same kind of shortcut than value for the terminals. And you also have a child 0, 1, 2, 3, 4, 5 if you want to get to the nth child directly, okay? So how does it work? BoostProto is trained to recognize this kind of types, function types inside, deconstruct it, and check what's going on. And that's where the things get interesting. It would take the written type of the function type, which is custom there, okay? And it will look at it and say, is it a callable object or not? If it's not, what I will do is take this type and call this constructor on it, and I will just build a new type, a new value. Sorry. But if the type is callable, I will just call its function operators with whatever is the evaluation of what's inside. So that's a massive shortcut to say, I want you to build a function object that just happened to extract the two children from the my plus expression, evaluate them, and then feed it to the custom function. Just a shortcut for saying this. So if Eric was there, he'd probably tell you that the funny thing is that BoostProto is actually a DSL for building DSLs. Because that's the kind of, syntactic sugar you want to put into a DSL so it looks cool, okay? Or give edX, depends. So let's call customs on the evaluation of my two sub-expression. And how is custom defined? Well, have a look there. So custom is a function object. So it's pre-C++ 11, okay? So bear with the good old result of kind of type deductions, okay? We have to flag it as callable by Proto. That's what the inheritance does on line 14. And that's return a double. It could have returned something more complex, okay? And you have these polymorphic operators function calls that take a t and a u and returns something which is t plus u times 100. Because that's really what you want to do with your language when you do plus. It really means t plus u times 100, okay, whatever. And whenever I match a plus, I will call that now. And what will be t and u? T and u will be, well, it will be whatever this part of the definition of the transform is. The evaluation of the left child for t and the evaluation of the right child for u. And I could actually, change all of this as much as I want. I could have another custom operator function object that I will put on top of custom and so on and so on and so on. You can build arbitrarily large and complex simile function call into this when construct. And Proto will just deconstruct it up to the beginning. So let's see how much is x plus 3 plus x times 3 under these rules. So it looks crooked. It's probably his. Okay. But he gets the jobs done. Yeah. Probably 50,600 something. So 2 times 3 is 6. 3 plus 2 is 5. So 5 plus 6 is whatever we saw upstairs. Okay. Oh, x plus 3 is not that. It's probably 2 plus 3 times 100. So that's 600. And 600 plus something. And so on and so on. So, but, well, we did that. We did this evaluation of the sub-expression before passing them to custom. But you're not obliged. What happens if I remove the eval before left and right? I would just pass the sub-expression to another function. Because what I want to do is maybe taking those two sub-expressions and generate another tree where they are put somewhere else. So we can actually write transform with Proto that say, I'm taking arbitrary parts of u and putting it into another place, another shape. And I just send you back another tree. Because that's what you need to do. So we can use this to arbitrarily deconstruct a tree and rebuild it in another way before passing it to another custom transform, for example. Okay. So you can do whatever you want. You're not forced to get the evaluation of whatever. You can just take the parts, construct them, reshape them in another way, and so on and so on. You have another versions of every of those plus, minus, and so on, which live in another namespace, which is proto-functional. And you can use this if you want to say, oh, whenever you match A plus B, I really want you to generate the tree A minus B. And you just say, when plus AB, return functional minus AB. You can just have those shortcut to say, I'm just pulling up, the subtree against one each other. Okay, so we can match a grammar, we can do transform on this, we have a pretty much set of defaults, we can write our own function to transforming whatever. But the problem is, what we endorse here are still what we call naked tree. The tree, the expression tree you manipulate there, has no frigging semantic. It's just a tree that happens to have all the operator you want, and you can turn it into whatever you want. But, for example, if you wanted to build one of those matrix-based DSLs, where is my operator parents to get to the ij element of my matrices? Or where is my dot size? Where is the actual semantic of the object I represent? They are not there. So we have to add it. So if you don't do anything else, what you have is a very nice stuff that builds arbitrary lazy tree and lets you manipulate the way you want, but you don't have any point where to put the semantic in. Well, except you have, but not yet. So how does it work when you want to add semantic on that? So we were basically up to 11. I think we will basically have to go to 12. Okay. So here is another more complete example. So I bring back the eval stuff that it just evaluates the expression the regular way. I bring back also the grammar that match if your type is correct. The concept that Proto puts forward is to say the following one. We need a way to say, I have a naked tree that is built using those set of rules. And I want to give it this kind of semantic by adding new members to the tree, member function. And the association of a rule set for building a tree and, let's say, the wrapping of the tree is what Proto calls a domain. Okay. A domain is something that says, whenever you build an expression this way, I want it to be wrapped with this kind of semantic. And whenever you call an operator on this decorated tree, what the operator does is remove the decorations, builds a naked tree, and put it back into the same wrapper. So you carry on the fact that if you have, for example, two matrices coming from the matrix domain, and you add them, you end up with a tree of an addition between two matrices of the matrix domain. And you could also have another domain called, for example, the vector domain. And the vector domain has a slightly different semantic. And you know that when you do a multiplication with an expression from the matrix domain and the vector domain, the resulting expression, well, where should it live? In the vector domain, because matrix times vectors give you a vector. So we can have different domains, and we can actually order them with some kind of relationships. And we can decide per operators, if I have a domain A and a domain B that come in, what's the domains that go outside. This is a way we can actually, oh, sorry for that. We can actually control the composite semantic of stuff, okay? Because, yeah, logically, this matrix times a vector doesn't have to live in the matrix domain. It's a vector, okay? So we have this strange notation. So let's make this forward declaration of expert. That will be our types with all the actual semantic. And we have this domain class, which is inheriting from BoostProto domain of BoostProto generator of expert EPA. That means what? That means that whenever you build an expression from this domain, I want you to generate it by wrapping it into expert. So you will take the type of my naked tree and put it there. Okay? But I want you to do this if and only if the tree you pass me is validated by this grammar, which is the second parameter of the domain. So if you write trap, okay, using expert, it won't compile, contrary to before. And what do we do now? So we have this link between the rule set and the wrappings, okay? You have the right to go into this box only if you match this kind of grammar. So what do? We just have to write the code for the box. So we write the code for expert. Is it okay for the Zoom? Yeah, correct? Okay. And what does it do? It inherits from BoostProto extends that say, I want you to extend this kind of tree types whenever it's wrapped inside myself, and I want you to enforce the rule of domain. Okay. And so this gives you a lot of boilerplates. Okay. So I'm just making a type def because I don't really want to write all this crap everywhere. So you basically need one thing. You need a constructor that takes the naked tree and put it into your box. It doesn't have to do much. Just pass it to your parent, okay, to proto extend. There is a bunch of macros that control the fact that if you want to have some special members handled by proto, so we want to use a sign with proto, so we use this macro. And I simplify the old return type issue, so I say we always return a double. And I have my small operator parents. Same thing than before. And what I do inside this is very trivial. I build an evaluator instance by using able, and I just call it on myself. Whenever you have an expression of something in Proto, it behaves as the something. So you can pass an expr of AST to an evaluator, and the evaluator will just strip the boxing and the wrapping and just work on the naked tree. So it's all transparent. Okay? It doesn't have to write into the grammar that you are wrapped into something. Okay? Then I make another type, which is a bit different. I'm tired of having to write terminal of something dot type. So I make another class which I call variable. And I say that a variable is an expression of a terminal of something. And whenever you pass me a value, I will just store it into the value of the terminal using this proto value function. There, 48. And I will add my own compression point, which was the operator, the assignment operator. I'm taking what? I'm taking an expr of x. And what do? I evaluate it using the function call operator, and I store the result into my value. Done. And I return this. Now what can I do? I can write this kind of things. I have a variable of n, it's x, is equal to 2, and y. And y is equal to x plus x times x plus 3. Let me print y using the evaluation operator. Okay? That's a bit, okay, it's a bit more complicated. Okay? So, Proto helps you build naked tree. Those naked tree has to be put into a box that gives you your actual language semantic. Your matrix as a size, your lazy string as an empty method, whatever. But it's referentially transparent. Proto doesn't care. Whenever you pass a boxed expression, sorry, a boxed tree to a match or to a transform, it will see through it and apply whatever you need. Okay. So we can separate everything. We separate the tree construction, which is completely independent. We have the tree traversals, and we have the tree semantic. And everything is independent and gets tied together by this notion of domain. Okay? So that's a bit more complicated than what we saw in the first session, where we're just pulling functions there and there, so everything worked. There, we have this level of abstraction that we have to think about. This is my grammar of my language. This is the semantic of my language elements. And this is the rules of transformation that bring me something from my expression in my languages to some value in the C++ world, or some types. Okay? So, session is over, I saw. So after the break, I will dip into a more intense example of Proto, which is already complete. Okay? Just to show you what kind of crooky things we can do. And we will speak about how we can actually do that probably a better way, and what are the limitations of still having in BoostProvo. Okay, and how we can probably find a way to wave them. Okay? So see you after the break if you still have any brain matter left.